So here's something to think about as you're lying there, getting comfortable, letting the day sort of dissolve behind you. Right now, in this exact moment, about 100 trillion neutrinos are passing through your body, every single second. Not per minute, not per hour, every second. They're streaming through your blanket, through the mattress, through the floor beneath you, through the entire earth itself, and out the other side. And they don't stop. They don't slow down. They barely even notice that any of it is there. You could put a wall of solid lead a light year thick in front of a neutrino, and most of them would sail right through it without so much as a nudge. They are, by almost any measure, the most ghostly, elusive, stubbornly invisible things in the entire universe, and yet they're real. They have mass. They carry energy. They helped shape the cosmos you live in. And the story of how we figured all of that out, how we went from not even knowing they existed to building enormous underground detectors just to catch a handful of them, that story is one of the strangest and most beautiful in all of physics. Let's start at the beginning. And I mean the real beginning, the place where the mystery first showed up. Because neutrinos weren't discovered the way most particles are discovered. Nobody saw one in a detector and said, "What's that?" No. Neutrinos were invented. They were imagined into existence by a desperate physicist who was trying to save one of the most fundamental laws in all of science. And the fact that he turned out to be right, that this ghost particle he dreamed up actually existed, well, that's one of those moments where the universe seems almost unreasonably cooperative. The year is 1930, and the problem is radioactive decay. Specifically, a type called beta decay. Now, if you're not sure what beta decay is, don't worry, we'll walk through it gently. Imagine you have an unstable atom. Its nucleus is carrying too many neutrons. It's not happy. It wants to become something more stable. So what it does is it converts one of its neutrons into a proton. And when that happens, the atom spits out an electron. That electron flying out of the nucleus, that's the beta particle. That's where the name comes from. Beta radiation. Scientists had known about this since the late 1800s. Henri Becquerel stumbled onto radioactivity in 1896, and within a few years, researchers like Ernest Rutherford were sorting the different types of radiation into categories: alpha, beta, gamma, based on how penetrating they were and how they behaved in magnetic fields. So beta decay was well established. The problem wasn't that it happened. The problem was the energy. Here's the thing. In physics, energy is supposed to be conserved. Always. No exceptions. You start with a certain amount of energy, and after whatever happens, you should end up with exactly the same total amount. This isn't just a guideline or a rough rule of thumb. Conservation of energy is one of the deepest, most battle-tested principles in all of science. It had never been violated. Not once. Not in any experiment anyone had ever done. And yet, when physicists carefully measured the energy of the electrons coming out of beta decay, something was wrong. The electrons should have all come out with the same energy. Think about it. You have a nucleus in a specific state. It decays to another specific state, and it releases an electron. The energy difference between those two states is fixed, so the electron should carry away a fixed amount of kinetic energy every time. Like a ball rolling off the same shelf, it always hits the ground with the same speed because the height of the shelf doesn't change. That's just conservation of energy doing its thing. But that's not what they saw. Instead of a single sharp energy value, the electrons came out with a whole spread of energies. Some had almost the full expected energy. Some had much less. Some had barely any at all. It was a continuous spectrum, a smooth curve, and it was deeply, deeply troubling. Now, you might think, okay, maybe the measurements were just sloppy. Maybe the detectors weren't precise enough. But these were careful experiments. Lisa Meitner and Otto Hahn in Berlin had been working on this since around 1911. James Chadwick, the same Chadwick who would later discover the neutron, confirmed the continuous spectrum in 1914 with meticulous measurements. By the mid-1920s, Charles Drummond Ellis and William Alfred Worcester at the Cavendish Laboratory in Cambridge had done what was essentially a definitive experiment. They used a calorimeter, basically a very precise heat-measuring device, to capture all the energy from the decay of bismuth-210, every single bit of it, and they showed that the average energy per decay was significantly less than the maximum. The missing energy wasn't hiding somewhere in the apparatus. It was genuinely gone. This was a crisis. And different physicists reacted to it in very different ways, and this is where it gets really interesting from a human standpoint, because you can see how people's personalities shape their scientific responses. Niels Bohr, the great Danish physicist, one of the founders of quantum mechanics, a towering figure in 20th century physics. Bohr looked at this problem and said, essentially, maybe energy just isn't conserved at the subatomic level. Maybe, in individual quantum events, energy conservation simply doesn't hold. It only works on average, statistically, when you look at lots of events together. Now, to modern ears, that sounds almost heretical, but Bohr was serious. He was genuinely willing to throw out conservation of energy. He'd already seen quantum mechanics overturn so many classical assumptions. Determinism, the idea that particles have definite positions and velocities at all times, that he figured, well, maybe energy conservation is next. Maybe it's another classical prejudice that doesn't survive the journey into the quantum world. And then there was Wolfgang Pauli. Pauli was Austrian, brilliant, sharp-tongued, famously critical, the kind of physicist who would read your paper and tell you it was not even wrong, meaning it was so muddled it couldn't even rise to the level of being incorrect. He was in his late 20s when the beta decay crisis was reaching its peak, and he was not willing to give up conservation of energy. Not for this, not for anything. But he also couldn't see any conventional way to explain where the energy was going. So on December 4th, 1930, he did something unusual. He wrote a letter. It's one of the most famous letters in the history of physics, and it's worth savoring for a moment. He addressed it to a group of physicists gathered at a meeting in Tübingen, Germany, and he began it, and I love this. He began it with, "Dear radioactive ladies and gentlemen." He couldn't attend the meeting in person, he explained, because he was indispensable at a ball in Zurich. You can hear the Pauli personality in every line. And then he laid out his desperate remedy, as he called it. He proposed that in beta decay, the nucleus emits not just an electron, but also a second particle, a new, unknown particle that carries away the missing energy. This particle would have to be electrically neutral, because the electric charge is already balanced without it. It would have to have very little mass, possibly no mass at all, and it would have to interact so weakly with matter that it had escaped detection in every experiment anyone had ever done. He called it the neutron, actually, the little neutral one. But that name was about to get taken. In 1932, James Chadwick discovered a much heavier neutral particle in the nucleus, and that became the neutron we know today. So the Italian physicist Enrico Fermi, who would play a huge role in this story very soon, gave Pauli's particle a new name. In Italian, the suffix "ino" means little, so Fermi called it the neutrino, the little neutral one, and the name stuck. But here's the thing. At this point, in the early 1930s, the neutrino was just an idea, a hypothesis, a placeholder for missing energy. Pauli himself was uncomfortable with it. He reportedly said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He even bet a case of champagne that no one would ever observe one. And you can understand his unease. A particle with no electric charge, barely any mass, that passes through matter as if it isn't there. How could you ever prove such a thing exists? It seemed almost unfalsifiable, which is the worst thing a scientific hypothesis can be. But Fermi believed in it. And Fermi was the kind of physicist who didn't just believe in things abstractly. He built theories around them. In 1933 and 1934, Fermi developed a comprehensive theory of beta decay that incorporated the neutrino as a real, physical particle. His theory described a new force of nature, what we now call the weak nuclear force or the weak interaction, and it explained beta decay as a process in which a neutron transforms into a proton by emitting both an electron and a neutrino, with the weak force mediating the whole event. The theory was elegant, it was quantitative, and it predicted the shape of that continuous energy spectrum almost perfectly. The spread of electron energies made complete sense if you assumed a second particle was sharing the energy. Sometimes the electron got most of it, sometimes the neutrino did, and all the possibilities in between traced out exactly the smooth curve that experimenters had been measuring for years. Fermi's theory was a masterpiece, and it was also a bit of a scandal. He submitted a paper on it to the journal Nature, and they rejected it. They said it was too speculative, too remote from reality. Fermi, who was not easily discouraged, published it in Italian and German journals instead, and it became one of the most important papers in 20th century physics. But the rejection tells you something about the mood of the time. Even with Fermi's beautiful mathematics, many physicists were skeptical. The neutrino was too convenient, too invisible, too perfectly designed to be undetectable. It felt like a cheat. And so the neutrino lived in a strange limbo for more than 20 years. Theorists used it freely. It made the math work. It saved conservation of energy. But experimentalists couldn't touch it, couldn't see it, couldn't prove it was real. It was like an imaginary friend that happened to be very good at arithmetic. Now, to understand why detection was so hard, and this is worth really sitting with, because it tells you something fundamental about what neutrinos are. You need to think about what it means for a particle to interact weakly. When we say a particle interacts with matter, we mean it exchanges force with other particles. Photons, particles of light, interact electromagnetically. They push on electrons, they get absorbed by atoms, they bounce off surfaces. That's why you can see light, why it heats your skin, why it exposes photographic film. Electromagnetic interactions are strong enough that photons almost never make it through any significant amount of matter without doing something. Neutrinos don't do any of that. They have no electric charge, so the electromagnetic force ignores them completely. They're not affected by the strong nuclear force either. That's the force that holds protons and neutrons together inside the nucleus. And it doesn't care about neutrinos. The only force that neutrinos feel, besides gravity, is the weak nuclear force. And the weak force is, well, weak. Fantastically, absurdly, almost comically weak. The probability of a neutrino interacting with an atom is so small that you'd need to line up roughly a light year of lead, about 10 trillion kilometers of solid lead, to have a 50-50 chance of stopping a single neutrino. One neutrino, one interaction, after traveling through 10 trillion kilometers of metal. So when those 100 trillion neutrinos pass through your body every second, essentially 0 of them interact with you. They don't ionize your atoms. They don't deposit energy. They don't trigger any chemical reactions. As far as your body is concerned, they're not there. And as far as a detector is concerned, they're not there either. Unless you build a very big detector, wait a very long time, and get very, very patient. That patience would eventually pay off. But it would take until the mid-1950s, a full quarter century after Pauli's letter, before anyone managed to catch a neutrino in the act. And the people who finally did it, two American physicists named Clyde Cowan and Frederick Rines. They didn't do it with some elegant tabletop experiment. They did it next to a nuclear reactor, one of the most powerful sources of neutrinos on Earth, using a detector the size of a large room buried underground, filled with hundreds of liters of liquid, surrounded by tons of shielding, running for months on end. And even then, they were catching only a few neutrinos per hour out of the inconceivable flood pouring out of that reactor. But I'm getting ahead of myself. Before we get to Cowan and Rines and their beautiful, painstaking experiment, there's something else happening in the 1930s and 1940s that matters. Because while the neutrino was sitting there as a theoretical ghost, the world was changing around it. Nuclear physics was accelerating at a breathtaking pace. Fission was discovered. The Manhattan Project happened. Nuclear reactors were built. And those reactors, it turned out, were neutrino factories on a scale that nobody had imagined before. A single large reactor, running at full power, produces something like 10 to the 20 neutrinos every second. That's 100 billion of them, every single second, streaming outward in all directions. And the reason is beautifully simple once you think about it. Inside a reactor core, you have uranium atoms splitting apart, and the fragments left behind, the fission products, are intensely neutron-rich. They have way more neutrons than stable nuclei want, so they undergo beta decay over and over, shedding that excess by converting neutrons into protons and releasing electrons and, crucially, antineutrinos. Each fission event ultimately leads to about 6 beta decays on average, and each of those beta decays produces one antineutrino. Multiply that by the staggering number of fissions happening every second in a reactor running at, say, a few hundred megawatts, and you get that incomprehensible flood. It's like someone turned on a fire hose, except the hose is spraying particles that pass through everything. Now, Frederick Rines was a fascinating character. He'd worked at Los Alamos during and after the war, and by the early 1950s, he was a theoretical physicist who had started thinking about what he called the really big questions, the fundamental problems that might actually be solvable with the tools that were becoming available. And one of the problems that kept nagging at him was this: can we actually detect the neutrino? It had been over 20 years since Pauli proposed the thing, and Fermi's theory had been enormously successful, and practically every physicist believed neutrinos were real, but nobody had ever directly seen one. It was still, in a very real sense, a particle that existed only on paper. Rines later said that the idea came to him in 1951, and the way he described it was almost poetic. He said he was thinking about what a physicist at Los Alamos could do that would be truly important, and the detection of the neutrino just rose to the top of the list. He recruited Clyde Cowan, an experimentalist with a gift for building things, for making equipment work in the real world, which is a talent that doesn't get nearly enough credit in physics. Cowan was practical, meticulous, and patient. The two of them made a wonderful team. Rines with the theoretical vision and Cowan with the hands to build it. Their first idea, and this is kind of wild, was to use a nuclear bomb. Seriously. They thought about detonating an atomic weapon and placing a detector nearby, not too nearby, obviously, to catch the enormous burst of neutrinos that would come out of the explosion. The flash of neutrinos from a nuclear detonation would be intense, but incredibly brief, and the idea was that you could distinguish the neutrino signal from background noise by its timing. You'd know exactly when the bomb went off, so you'd look for events in your detector at precisely that moment. They actually got fairly far in planning this. They called it Project Poltergeist, which is a perfect name when you think about it, hunting for a ghost. But eventually, they realized that a reactor was a better bet. A bomb gives you one shot, one enormous pulse, and if anything goes wrong with your detector in that moment, you've wasted a nuclear explosion. A reactor, on the other hand, just sits there running, day after day, week after week, producing a steady, continuous stream of antineutrinos. You can take your time. You can calibrate. You can troubleshoot. You can run control experiments with the reactor turned off and compare them to data taken with the reactor running. It's just a much more forgiving experimental setup. So they pivoted to using a reactor, and that decision made all the difference. Here's the thing about detecting a neutrino, or more precisely, an antineutrino, which is what reactors produce. You need to find a reaction where the antineutrino actually does something observable. And the reaction Cowan and Reynes chose was inverse beta decay. It's the reverse of ordinary beta decay, and it works like this. An antineutrino comes along and hits a proton, just a plain hydrogen proton, sitting in some target material. The antineutrino interacts with that proton through the weak force, and the proton converts into a neutron while emitting a positron. That positron is the antimatter counterpart of the electron. Same mass, opposite charge. So you've got two products, a positron and a neutron. And here's what's really clever about Cowan and Reynes' approach. They figured out how to detect both products and the combination of the two, arriving in a specific sequence with a specific time delay, became their signature. Their fingerprint for saying yes, that was a neutrino. Let me walk you through how that works, because it's genuinely elegant. The positron, the moment it's created, almost immediately encounters an electron in the surrounding material. And when matter meets antimatter, they annihilate each other. The positron and the electron both disappear, and their combined mass gets converted into energy in the form of two gamma rays, two photons of very specific energy, 0.511 million electron volts each, flying off in opposite directions. That's a direct consequence of conservation of energy and momentum. Two gamma rays, back to back, each with a precise energy. That's your first signal. Now the neutron. The neutron is slower. It bounces around in the detector material for a little while, losing energy with each collision, thermalizing. That's the term. It just means slowing down to the ambient thermal energy of the surrounding atoms. And then, after a few microseconds, maybe 5, maybe 10, it gets captured by a nucleus. Cowan and Reynes dissolved cadmium chloride in their target liquid because cadmium is exceptionally good at capturing slow neutrons. Cadmium has an enormous neutron capture cross-section, which is just a way of saying it's very hungry for neutrons. When a cadmium nucleus swallows that neutron, it gets excited and releases that excess energy as a burst of gamma rays, a cascade of them, with a total energy of about 9 million electron volts. So the signature of a neutrino event is this. First, you see two simultaneous gamma rays from the positron annihilation. Then, a few microseconds later, you see a second burst of gamma rays from the neutron capture on cadmium. That 1-2 punch, that delayed coincidence, is extraordinarily distinctive. Random background events, cosmic rays, natural radioactivity, electrical noise, might occasionally mimic one of those signals, but the odds of a random event producing both signals in the right sequence with the right time delay are vanishingly small. That's how you pull a neutrino signal out of the noise. You're not looking for a single flash. You're looking for a very specific pattern. And this is where Cowan's engineering talent really shone. They built a detector using large tanks of liquid scintillator, a special liquid that produces tiny flashes of light when a gamma ray passes through it and interacts with the atoms inside. Those flashes of light were picked up by photomultiplier tubes, which are these remarkable devices that can take a single photon, just one particle of light, and amplify it into a measurable electrical signal. The detector was layered like a sandwich. They had tanks of target liquid, water with dissolved cadmium chloride, providing the protons for the anti-neutrinos to hit and the cadmium to capture the neutrons, sandwiched between tanks of liquid scintillator, lined with photomultiplier tubes to catch the gamma rays. Their first real attempt was in 1953 at the Hanford reactor in Washington State. They set up their detector, and they did see a signal, a small excess of delayed coincidence events when the reactor was running compared to when it was off. But the signal-to-noise ratio was poor. There was too much background, too much cosmic ray interference. They could claim evidence for the neutrino, and they did, cautiously, but it wasn't definitive. It wasn't the kind of clean, unambiguous result that would convince every skeptic. So they moved. They relocated the entire experiment to the Savannah River plant in South Carolina, where a more powerful reactor was available and, crucially, where they could place their detector underground beneath the reactor, with the reactor building itself and the earth above acting as a shield against cosmic rays. They also made the detector bigger and better, more scintillator, more photomultiplier tubes, better shielding. They surrounded the whole thing with lead and paraffin to block stray radiation. They improved their electronics to get better time resolution on that delayed coincidence measurement. Every detail was refined. And then they ran. For months, patiently accumulating data, counting those telltale double flashes, comparing reactor on periods to reactor off periods, and the result was clear. They were seeing about 3 events per hour that matched the neutrino signature, and the rate dropped to essentially 0 when the reactor was shut down. 3 per hour. Think about that. The reactor is flooding the detector with something like 10 trillion antineutrinos per second passing through it, and they're catching 3 per hour. That's how weak the weak force really is. That's how ghostly these particles are. But 3 per hour was enough. It was a real, reproducible, statistically significant signal. On June 14, 1956, Cowan and Raines sent a telegram to Wolfgang Pauli. It read, in essence, "We are happy to inform you that we have definitively detected the neutrino." Pauli, by all accounts, was thrilled. He reportedly drank an entire case of champagne with his friends that night. And why wouldn't he? 26 years after he'd written that apologetic letter proposing a particle he thought might never be found, 2 experimentalists with extraordinary patience and cleverness had pulled it out of the noise. The ghost was real. Raines would eventually receive the Nobel Prize for this work in 1995, nearly 40 years after the experiment, and sadly, Cowan had died in 1974 and couldn't share it. The Nobel Committee doesn't award prizes posthumously, which is one of those quiet injustices that runs through the history of physics. Cowan deserved that prize as much as anyone. But here's something interesting that was happening at almost exactly the same time Cowan and Reynes were chasing reactor antineutrinos. On the other side of the world, in a sense, other physicists were starting to wonder about a different question entirely. Not whether neutrinos exist, that was being settled, but whether there might be more than one kind of neutrino. Because by the mid-1950s, there was a new particle in town that was behaving in ways that seemed to demand its own neutrino, the muon. And the story of the muon is one of those delightful episodes in physics where nature hands you something completely unexpected, something nobody asked for, and then you spend the next 50 years trying to figure out where it fits. The muon showed up uninvited, and honestly, it confused everybody. So let's back up a little. In the 1930s, physicists were trying to understand cosmic rays, these high-energy particles that rain down on Earth from space. They'd send up balloon experiments, or they'd go to mountaintops with cloud chambers, which are these beautiful devices where charged particles leave visible trails of condensation as they pass through supersaturated vapor. You could actually see the paths of subatomic particles. And in 1936, Carl Anderson and Seth Nettermeyer, working at Caltech, found something in their cloud chamber photographs that didn't match anything they knew about. There were tracks that curved in the magnetic field more than an electron would, but less than a proton would. Whatever was making these tracks had a mass somewhere in between, roughly 200 times heavier than an electron, but much lighter than a proton. And it carried a negative charge, just like an electron. Now here's the thing. At first, people thought this might be the particle that the Japanese theorist Hideki Yukawa had predicted just a year earlier. Yukawa had proposed that the strong nuclear force, the force that holds protons and neutrons together inside an atomic nucleus, should be mediated by a particle with a mass of roughly that size. So when Anderson and Nettermeyer found a particle in that mass range, the natural assumption was, great, that's Yukawa's particle, mystery solved. But it wasn't. It really wasn't. The problem became clear over the next decade. If this particle were truly the carrier of the strong force, it should interact strongly with atomic nuclei. That's the whole point. It's supposed to be the glue. But experiments kept showing that this new particle passed through matter far too easily. It barely interacted with nuclei at all. It was penetrating, ghostly in its own way. There's a famous remark, often attributed to the physicist E.I. Rabi, who when told about the muon, reportedly said, "Who ordered that?" And that line has become one of the most quoted in all of particle physics because it captures the genuine bewilderment. Nobody had predicted this particle. Nobody needed it. It didn't seem to do anything useful. It was just there. By the late 1940s, it became clear that there were actually two different particles hiding in cosmic rays. One of them was Yukawa's particle, the pion, which does interact strongly and does mediate the nuclear force. The other was this penetrating thing, the muon, which is essentially a heavier copy of the electron. Same charge, same spin, same types of interactions. It feels the electromagnetic force and the weak force, but not the strong force. It's just 207 times heavier. And it's unstable. A muon lives for about 2.2 microseconds before it decays. That's actually a pretty long time by particle physics standards, long enough that muons from cosmic ray showers can reach the ground, which is why they were discovered in the first place. So here's the question that started nagging at people. When a muon decays, what does it decay into? Well, it decays into an electron, And it also produces two other particles, neutral ones, invisible ones, that carry away energy and momentum. And those neutral particles looked, by all accounts, like neutrinos. But here's what's interesting. If the muon is just a heavy electron, and if there's only one kind of neutrino, then you'd expect certain reactions to happen that don't. Specifically, if a muon is really just a fat electron and neutrinos are all the same, then you should be able to observe certain decay modes and certain scattering processes that nobody was seeing. There seemed to be some kind of selection rule at work, some hidden conservation law that was preventing certain things from happening. By the late 1950s, several theorists, including Bruno Pontecorvo, who we'll come back to because he's an absolutely fascinating character, were suggesting that maybe the neutrino associated with the muon is a different particle from the neutrino associated with the electron. Maybe there are two kinds of neutrinos, an electron neutrino and a muon neutrino. And the reason you never see certain reactions is that these two flavors, as they came to be called, are genuinely distinct. They carry different quantum numbers. Nature keeps track of which is which. Now, that's a bold claim. How do you test it? You'd need to create a beam of neutrinos that you know came from muon-related processes, and then see what happens when those neutrinos interact with matter. If there's only one kind of neutrino, those neutrinos should be able to produce both electrons and muons when they interact. But if the muon neutrino is truly different from the electron neutrino, then a beam of muon neutrinos should only produce muons, never electrons. That's the test. Clean, simple in concept, extraordinarily difficult in practice. And this is where we come to one of the great experiments in 20th century physics. It took place at Brookhaven National Laboratory on Long Island, New York, in 1962. The team was led by three physicists, Leon Lederman, Melvin Schwartz, and Jack Steinberger. And the story of how this experiment came together is worth telling, because it illustrates something important about how physics actually works. Sometimes the breakthrough isn't a new theory or a new particle. It's a new method, a new way of looking. Melvin Schwartz was a young faculty member at Columbia University, and the idea came to him, at least in part, during a conversation at a coffee lounge. The key insight was this: particle accelerators had gotten powerful enough by the early 1960s that you could slam high-energy protons into a target and produce enormous numbers of pions. Pions decay into muons and neutrinos. If you could let the pions decay in flight and then put enough shielding in the way to stop everything except neutrinos, stop the muons, stop the leftover pions, stop everything that interacts with matter, then whatever comes out the other side of that wall of shielding is a beam of neutrinos. A neutrino beam. And specifically, since the pions decay into muons and neutrinos, these would be neutrinos produced in association with muon neutrinos, if such a thing exists. The shielding they used was extraordinary. They stacked about 40 feet of steel, old battleship armor plates from the Brooklyn Navy Yard, actually, which is a wonderful detail. 13.5 meters of solid steel. Enough to stop everything. Protons, pions, muons, photons, everything gets absorbed. Everything except neutrinos, which sail through 40 feet of steel like it isn't there. On the far side, they placed a 10-ton aluminum spark chamber detector, which could reveal the tracks of charged particles produced when a neutrino occasionally interacted with an aluminum nucleus. Think about what they're doing here. They're creating the world's first artificial neutrino beam, filtering out everything else with a wall of battleship armor, and then watching for the incredibly rare moments when one of those neutrinos deigns to interact. And the question is simple. When a neutrino from this beam interacts and produces a charged particle, is that particle a muon or an electron? If it's always a muon, never an electron, then the muon neutrino is genuinely different from the electron neutrino. 2 flavors. The experiment ran for about 8 months. They observed a total of roughly 56 neutrino interaction events. Not 56,000. 56. And of those, the vast majority produced muons. They saw clear muon tracks, long, penetrating, characteristic, and they saw essentially no electrons. The occasional ambiguous event, sure, but nothing consistent with electron production. The conclusion was striking and unambiguous. The neutrinos produced alongside muons are not the same as the neutrinos produced alongside electrons. There are 2 distinct types. The muon neutrino is real. This was a huge deal. It meant the particle zoo was richer than anyone had hoped or feared. It meant that the organization of matter into families or generations was deeper than just the electron and its heavier cousin, the muon. Each one came with its own neutrino partner. And it opened the door to a question that would haunt physics for decades. Are there even more? Could there be a third kind? A fourth? Liederman, Schwartz, and Steinberger received the Nobel Prize in Physics in 1988 for this work. And beyond the specific discovery, their experiment established a technique, the neutrino beam, that would become one of the most powerful tools in particle physics. Almost every major neutrino experiment since then has relied on some version of this idea. You make neutrinos by smashing protons into targets, you let pions and kaons decay, and you use hundreds of meters of rock or steel to filter out everything that isn't a neutrino. It's brute force and elegance at the same time. But let's sit with this result for a moment, because it raises a philosophical point that's kind of beautiful. The muon, remember, was the particle nobody ordered. It showed up uninvited, looking like a pointless copy of the electron, and now it turns out that it brought its own neutrino with it. Nature didn't just make a heavier electron for no reason. It made an entire family. An electron neutrino, a muon neutrino, paired up, organized. There's a structure here, a pattern, even if nobody in the early 1960s could fully explain why. And here's where the story takes another turn that nobody saw coming. Remember Bruno Pontecorvo? I mentioned him a minute ago and said we'd come back to him. Pontecorvo is one of the most extraordinary and tragic figures in the history of neutrino physics. Born in Italy in 1913, he was a student of Enrico Fermi, one of the famous Via Panisperna boys, that brilliant group of young physicists in Rome in the 1930s. Pontecorvo was gifted, creative, and had an almost uncanny physical intuition. After the war, he worked in Canada and then Britain on nuclear reactor physics. But in 1950, at the height of Cold War paranoia, Pontecorvo defected to the Soviet Union. Just vanished. He and his family disappeared during a vacation in Italy, and the Western intelligence services went into a panic because Pontecorvo had worked on classified nuclear projects. For years, nobody in the West knew where he was or even whether he was alive. He resurfaced in the Soviet Union, where he continued to do physics, brilliant physics, but largely cut off from the Western scientific community. And it was Pontecorvo who, as early as 1957, had suggested the two neutrino idea and proposed something even more radical. He wondered whether neutrinos might be able to transform from one type into another, whether an electron neutrino, traveling through space, might spontaneously become a muon neutrino and then change back again. He called this neutrino oscillation. And if it sounds strange, it is. It's one of the most quantum mechanical things you can imagine. A particle literally changing its identity as it travels, not decaying into something else, not interacting and being converted, but just becoming a different kind of particle all on its own as a consequence of quantum mechanics. Now, in the early 1960s, this was a speculative idea. Most physicists didn't take it too seriously. Oscillation requires something very specific to be true. The different neutrino flavors would have to have slightly different masses, and at the time, most people assumed neutrinos were massless, just like photons. If they're massless, they can't oscillate. End of story. So Pontecorvo's idea sat there, quietly, on the margins. A beautiful theoretical possibility that most people filed away and forgot about. But nature, as it turns out, had other plans. And the first hint that something was deeply wrong with our understanding of neutrinos came not from a particle accelerator or a nuclear reactor, but from the sun. Because in the mid-1960s, a chemist named Ray Davis was getting ready to do something audacious. He was going to try to catch neutrinos streaming out of the sun's core, and he was going to do it with a swimming pool's worth of cleaning fluid, dry cleaning fluid, to be specific, perchloroethylene, the same stuff you'd find at your local dry cleaner. About 100,000 gallons of it, sealed inside a massive tank, buried nearly a mile underground in a gold mine in South Dakota. The Homestake Mine, in the town of Lead. And if that sounds like an unusual way to do particle physics, well, that's because it was. But Ray Davis had thought it through very carefully, and the logic was actually quite beautiful. Here's the setup. The sun, as you probably know, is basically a giant nuclear furnace. Deep in its core, hydrogen nuclei are being fused together to make helium, and this process releases enormous amounts of energy. That's what makes the sun shine. But fusion doesn't just produce light and heat. It also produces neutrinos, electron neutrinos, specifically. Billions and billions of them, every second, streaming outward from the sun's core at nearly the speed of light. And because neutrinos barely interact with anything, they pass straight through the sun's outer layers as if they weren't even there. They cross the 93 million miles of space between the sun and the Earth in about 8 minutes, and then they pass through the Earth too. Right now, as you're lying there, something like 65 billion solar neutrinos are passing through every square centimeter of your body every single second. You don't feel a thing. They're like ghosts made of almost nothing. So Ray Davis wanted to catch some of these ghosts, and the way he planned to do it relied on a very specific nuclear reaction. If an electron neutrino happens to hit a chlorine-37 atom, one of the isotopes of chlorine in that cleaning fluid, there's a tiny, tiny chance it will convert a neutron inside the chlorine nucleus into a proton. That transforms the chlorine-37 into argon-37. And argon is a noble gas, so it doesn't bond with anything. It just sits there, a single atom of argon floating in this ocean of cleaning fluid. Davis's plan was to let the tank sit for a couple of months, let the solar neutrinos do their thing, and then extract the argon atoms and count them. Now think about what that means. You've got 100,000 gallons of liquid. You're looking for maybe a handful of atoms, literally a few dozen atoms of argon, produced over the course of weeks. It's like dumping a thimble of special sand into a swimming pool, and then coming back a month later to find every single grain. The precision required was extraordinary, and Davis, who was a radiochemist at Brookhaven National Laboratory, was one of the very few people in the world who had the skills to pull it off. He'd been developing these techniques for years, learning how to extract vanishingly small quantities of noble gas atoms from large volumes of liquid. He was meticulous, patient, and stubborn in the best possible way. The reason the experiment was underground, by the way, was to block cosmic rays. Up on the surface, high-energy particles from space are constantly raining down, and they'd create all sorts of nuclear reactions in the cleaning fluid that would swamp the signal. But a mile of rock overhead acts as a natural shield. Almost nothing can penetrate that much solid Earth. Nothing except neutrinos, of course. So by going deep underground, Davis could be reasonably confident that any argon-37 he found was produced by neutrinos, not by cosmic ray contamination. The experiment started collecting data in 1968. And here's where the story gets really interesting. Davis did detect solar neutrinos. He proved they were real, proved they were coming from the sun, proved that the nuclear fusion reactions powering the sun were actually happening the way physicists thought. That alone was a triumph. But there was a problem. He wasn't finding enough of them. Not nearly enough. See, by this time, an astrophysicist named John Bacall had built a detailed theoretical model of the sun, a mathematical description of everything happening in the solar interior, the temperatures, the pressures, the rates of various nuclear reactions. Bacall's model predicted how many neutrinos the sun should be producing and, therefore, how many argon atoms Davis should be finding in his tank. And when they compared the prediction to the measurement, Davis was only seeing about 1/3 of the expected number. Roughly 1/3 of the neutrinos were missing. This became known as the solar neutrino problem, and it would haunt physics for the next 30 years. 30 years. Think about that. An entire generation of physicists grew up with this puzzle hanging over the field, and nobody could definitively solve it. Now, the immediate reaction from a lot of people was to assume someone had made a mistake. Either Davis's experiment was wrong, maybe he wasn't extracting all the argon, maybe there was some systematic error in his chemistry, or Bacall's solar model was wrong, maybe the temperature at the sun's core was slightly different than predicted, which would change the neutrino production rates, and both of those were reasonable possibilities. Davis spent years checking and rechecking his methods. Bacall spent years refining his solar model. Other people built different kinds of solar models, and the discrepancy stubbornly refused to go away. The numbers kept coming back the same way, about 1/3 of the expected neutrinos, give or take. And this is where Pontecorvo's old idea starts whispering from the margins. Because there was a third possibility, one that most people were reluctant to take seriously at first. What if the sun was producing exactly the right number of electron neutrinos, just as Bacall predicted, but some of them were changing into muon neutrinos, or even some other type of neutrino during their journey from the sun to the Earth? Davis's chlorine detector could only see electron neutrinos. That was the specific reaction, chlorine-37 capturing an electron neutrino. If some of those electron neutrinos had oscillated into a different flavor, by the time they reached South Dakota, they'd pass right through the cleaning fluid without triggering the reaction. They'd be invisible to Davis. The neutrinos wouldn't be missing. They'd just be wearing a disguise. It was an elegant explanation, almost too elegant, and it required neutrinos to have mass, which was still considered unlikely by most of the physics community. The standard model of particle physics, which was being assembled and refined throughout the 1970s, treated neutrinos as massless particles. Giving them mass would mean the standard model was incomplete. And people had invested a lot of intellectual capital in the standard model. It explained so many things so well. The idea that it might be wrong about something as fundamental as whether neutrinos have mass, that was a big deal. So the solar neutrino problem sat there, unresolved, like a splinter you can't quite get out. Davis kept running his experiment. Pauli kept refining his models. They became close friends and collaborators, the experimentalist and the theorist, united by this shared obsession. Pauli once said that he spent his entire career trying to understand why Davis's experiment disagreed with his calculations. It's a remarkable thing. Two scientists, working on the same problem for decades, pushing each other, challenging each other, never quite getting to the answer during the years when they were working most actively together. Meanwhile, other experiments started coming online. In the late 1980s and into the 1990s, new detectors were built that could look at solar neutrinos in different ways. The Kamiokande detector in Japan, which we should talk about because it's a marvel of engineering in its own right, used a completely different approach. Instead of a chemical reaction, Kamiokande used a huge tank of ultra-pure water surrounded by thousands of extremely sensitive light detectors called photomultiplier tubes. When a neutrino scattered off an electron in the water, the electron would recoil at high speed, faster than the speed of light in water. And when a charged particle moves faster than light in a medium, it produces a faint cone of blue light called Cherenkov radiation, the optical equivalent of a sonic boom. The photomultiplier tubes would catch that faint flash of light, and from the pattern of the flash, you could figure out the direction the neutrino came from, and roughly how much energy it had. Kamiokande confirmed Davis's result. The solar neutrino deficit was real. And because Kamiokande could determine the direction the neutrinos were coming from, it proved definitively that they were arriving from the sun. Not from some other source, not from some background contamination, from the sun. So the neutrinos were definitely there, they were definitely solar, and there were definitely too few of them. Then came the Soviet-American gallium experiment, called SAGE, and a European experiment called GALEX, both using gallium instead of chlorine. Gallium detectors were sensitive to lower energy neutrinos than Davis's chlorine detector, which meant they could see the neutrinos from the most fundamental fusion reaction in the sun, the proton-proton chain, which is the dominant energy source. And guess what? Same story. Too few neutrinos. About half the expected number this time, but still a clear deficit. By the mid-1990s, the evidence was piling up. Multiple experiments using different techniques, different target materials, in different locations around the world, all seeing fewer electron neutrinos from the sun than theory predicted. The chance that all of them were making the same mistake was getting harder and harder to believe. And the solar models kept getting better, kept being confirmed by other observations, like measurements of how sound waves propagate through the sun's interior. A field called helioseismology, which is a gorgeous word and an even more gorgeous science. The sun rings like a bell, and by studying those vibrations, you can map its internal structure with remarkable precision. And the helioseismology data agreed beautifully with Pauli's models. The sun was behaving exactly as predicted. It was the neutrinos that were doing something unexpected. So the spotlight was slowly, inexorably turning toward Pontecorvo's old idea. Neutrino oscillation. Maybe the neutrinos really were changing flavor. Maybe they really did have mass. And if that was true, it would be one of the first concrete pieces of evidence that the standard model, for all its successes, was not the complete story of particle physics. That there was new physics lurking just beyond its edges. But proving oscillation directly, that was going to take something more. You couldn't just show that electron neutrinos were disappearing. You had to show where they were going. You had to either catch them arriving as a different flavor or demonstrate the oscillation pattern in a way that couldn't be explained by anything else. And the experiment that would finally crack this open wasn't looking at the sun at all. It was looking at something much closer and, in a way, much stranger. It was looking at neutrinos produced in the Earth's own atmosphere, created when cosmic rays slam into air molecules high above our heads. And the detector that would make this discovery was a successor to Kamiokande, a scaled-up version so ambitious that they simply called it Super-Kamiokande. 50,000 tons of ultra-pure water, 11,000 photomultiplier tubes, each one the size of a beach ball, lining the walls and floor and ceiling of a cylindrical cavern carved out of Mount Ikanoyama in Japan. Picture that for a second. Each photomultiplier tube about 50 centimeters across, and there are 11,000 of them, all pointing inward, all staring at this enormous volume of water, waiting for the faintest possible flash of blue light. Cherenkov radiation, that same trick Kamiokande had used. When a charged particle moves through water faster than light travels through water, it produces a cone of light, like a sonic boom but made of photons. And by reading the pattern of which tubes fire and when, you can reconstruct the direction the particle came from, its energy, and crucially, what kind of particle it was. Super-Kamiokande began taking data in 1996, and the team there, led by Takaaki Kajita, wasn't just looking at solar neutrinos. They were looking at atmospheric neutrinos, and this is where the story takes a really beautiful turn. So let's talk about what atmospheric neutrinos are and why they turned out to be exactly the right tool for the job. When a cosmic ray, usually a high-energy proton, comes screaming in from outer space and hits a nitrogen or oxygen nucleus high in the atmosphere, it creates a shower of secondary particles, pions mostly, and those pions decay. A charged pion decays into a muon and a muon neutrino. Then the muon itself decays into an electron neutrino, and another muon neutrino. So if you count up the neutrinos produced in this chain, you'd expect roughly 2 muon neutrinos for every 1 electron neutrino. That ratio, about 2-to-1, is a pretty robust prediction. It doesn't depend on knowing exactly how many cosmic rays are hitting the atmosphere or precisely what energies they have. The ratio is determined by the decay physics, and the decay physics is well understood. So even if you're uncertain about the total number of atmospheric neutrinos, you can be quite confident about the ratio of muon neutrinos to electron neutrinos. And here's where it gets clever. Super-Kamiokande could tell the difference between muon neutrinos and electron neutrinos because of the particles they produce when they interact. An electron neutrino hits a nucleus in the water and produces an electron, which creates a fuzzy, diffuse ring of Cherenkov light. A muon neutrino produces a muon, which creates a sharp, clean ring. The detector could distinguish between those two patterns with impressive reliability, so they could count muon neutrino events and electron neutrino events separately. And what they found was that the electron neutrinos looked fine. The number they detected matched predictions pretty well. But the muon neutrinos, they were missing. Not all of them, but a significant fraction. And here's the part that made everyone sit up straight. The deficit depended on where the neutrinos were coming from. Think about this. Cosmic rays hit the atmosphere from all directions, more or less uniformly. So atmospheric neutrinos are being produced all around the Earth all the time. Some of those neutrinos are created in the atmosphere directly above the detector in Japan. Those travel maybe 15 or 20 kilometers straight down before reaching Super-Kamiokande. But others are created on the far side of the Earth, in the atmosphere above, say, Argentina or South Africa, And those neutrinos travel all the way through the planet, about 13,000 kilometers, before reaching the detector from below. Now, if neutrinos are just neutrinos and nothing funny is happening, it shouldn't matter how far they've traveled. You should see roughly the same rate from above as from below, adjusted for geometry. But Super-Kamiokande saw something dramatically different. The muon neutrinos coming from directly overhead arrived in the expected numbers. The muon neutrinos coming from below, the ones that had traveled through the entire Earth, were depleted. About half of them were gone. And it wasn't a cliff. It was a gradient. The farther the neutrinos had traveled, the more muon neutrinos were missing. Neutrinos coming from the horizon, which travel a few hundred kilometers through the atmosphere, showed an intermediate deficit. It was a smooth, distance-dependent disappearance pattern. And that pattern, that beautiful, unmistakable pattern, is exactly what you'd expect from neutrino oscillation. Let me explain why. Remember Pontecorvo's idea. If neutrinos have mass, and if the mass states don't perfectly line up with the flavor states, then a neutrino born as one flavor will gradually shift into another flavor as it travels. The probability of it being detected as its original flavor oscillates. It goes up and down like a wave. And the key variables are the distance traveled and the neutrino's energy. More distance means more time for oscillation. Lower energy means faster oscillation. The specific mathematical relationship involves the ratio of distance to energy and the squared difference of the masses of the two mass states involved. So when Super-Kamiokande saw muon neutrinos disappearing in proportion to how far they'd traveled, with the downward-going ones intact and the upward-going ones depleted, it was like watching the oscillation happen in real time. The atmosphere was producing muon neutrinos at a known ratio. The short-distance ones arrived as expected. The long-distance ones had oscillated away, most likely into tau neutrinos, which Super-Kamiokande couldn't easily detect because tau particles are very heavy and require a lot of energy to produce. Kajita presented these results at the Neutrino 98 conference in Takayama, Japan, in June of 1998, and the reaction was extraordinary. The data was clean, the statistics were strong, and the conclusion was almost inescapable. Neutrinos oscillate. Neutrinos have mass. The audience gave a standing ovation, which, if you know anything about physics conferences, is not something that happens often. Physicists are not generally a standing ovation crowd. And think about what that means. For decades, the Standard Model had assumed neutrinos were massless. It was one of those assumptions that had been baked in from the beginning, partly for simplicity, partly because no one had ever measured a neutrino mass, and partly because the theoretical framework didn't require them to have mass. But Super-Kamiokande had just shown with overwhelming evidence that at least one neutrino mass state had to be different from at least one other. The squared mass difference was tiny, on the order of a few thousandths of an electron volt squared, but it was not zero. And if the squared mass difference is not zero, then at least one of the masses is not zero. The Standard Model, the most successful theory in the history of physics, was incomplete. Now, while Super-Kamiokande was making this discovery with atmospheric neutrinos, the solar neutrino problem was still hanging there, right? Davis had seen the deficit. Kamiokande had confirmed it. The gallium experiments had confirmed it at lower energies. But all of those experiments could only detect electron neutrinos. If the solar electron neutrinos were oscillating into muon or tau neutrinos, those experiments would simply miss them. What you really wanted was a detector that could see all three flavors. A detector that could say, look, the total number of neutrinos from the sun is exactly what Bacall predicted. They're all there. They've just changed costume. And that's exactly what the Sudbury Neutrino Observatory did. SNO, as everyone called it, was built 2 kilometers underground in an active nickel mine near Sudbury, Ontario, in Canada. It used 1,000 tons of heavy water, deuterium oxide, water where the hydrogen atoms have an extra neutron. And heavy water was the key to the whole thing, because it allowed SNO to detect neutrinos in 3 different ways. The first was the charged current interaction, where an electron neutrino hits a deuterium nucleus and converts the neutron into a proton, producing an electron. This reaction is sensitive only to electron neutrinos. The second was the neutral current interaction, where a neutrino of any flavor hits the deuterium nucleus and simply breaks it apart into a proton and a neutron without producing a charged lepton. This reaction is equally sensitive to all 3 flavors: electron, muon, and tau. And the third was elastic scattering, where a neutrino bounces off an electron, which is sensitive to all flavors, but mostly to electron neutrinos. So by comparing the charged current rate, which counts only electron neutrinos, with the neutral current rate, which counts all neutrinos regardless of flavor, you could directly measure whether the missing electron neutrinos had transformed into something else. If the total flux from the neutral current measurement matched Bach-Hall's prediction, while the charged current measurement showed a deficit, that would be proof that the neutrinos were oscillating, not disappearing. And in 2001 and 2002, SNO published its results, and they were stunning. The charged current measurement showed about 1/3 of the predicted electron-neutrino flux, consistent with what Davis and Kamiokande had seen for decades. But the neutral current measurement showed a total neutrino flux that was completely consistent with Bach-Hall's solar model predictions. All the neutrinos were there, every last one of them. They'd just changed flavor on the way from the core of the sun to the mine in Sudbury. John Bach-Hall, who had spent 30 years defending his solar model, who had endured skepticism and doubt and the quiet implication that maybe his calculations were wrong, Bach-Hall was vindicated, completely, beautifully vindicated. And Ray Davis, who had spent those same 30 years patiently counting argon atoms in a tank of cleaning fluid a mile underground, was vindicated too. Davis shared the 2002 Nobel Prize in Physics with Masatoshi Koshiba, who led the Kamiokande experiment. Bach-Hall, heartbreakingly, did not share in the prize. The Nobel Committee recognized the experimentalists, though virtually everyone in the field acknowledged that his theoretical work was essential to the entire discovery. Bach-Hall passed away in 2005, widely regarded as one of the great astrophysicists of his generation. And Takaaki Kajita of Super-Kamiokande and Arthur MacDonald of SNO shared the 2015 Nobel Prize in Physics for the discovery of neutrino oscillations, which showed that neutrinos have mass. 2 experiments, 2 different sources of neutrinos, one atmospheric, one solar, both pointing to the same revolutionary conclusion. The standard model needed to be extended. Neutrinos were not what we thought they were. But here's the thing. Knowing that neutrinos oscillate and knowing the details of how they oscillate are 2 very different things. Super-Kamiokande had measured 1 mass splitting, the difference between 2 of the 3 mass states related to atmospheric neutrino oscillation. SNO and the solar experiments had measured another mass splitting, a much smaller one related to solar neutrino oscillation. But the full picture of neutrino mixing involves a 3x3 matrix, a mathematical object called the PMNS matrix, named after Pontecorvo, Maki, Nakagawa, and Sakata, who worked out the theoretical framework. This matrix has 3 mixing angles and a phase that could produce something called CP violation, which is a difference in behavior between matter and antimatter. By the early 2000s, 2 of the 3 mixing angles were reasonably well measured. The atmospheric mixing angle, called theta 23, was large, close to 45 degrees, meaning nearly maximal mixing. The solar mixing angle, theta 12, was also large, around 34 degrees. But the third angle, theta 13, was unknown. It could have been 0, which would have meant a simpler mixing pattern and no possibility of CP violation in the neutrino sector. Or it could have been small but non-zero, which would have opened the door to some of the most profound questions in physics, including potentially why the universe contains more matter than antimatter, and measuring theta 13 became one of the great experimental races of the early 21st century, a race that would involve nuclear reactors, mountains, and some of the most precise detectors ever built. So let's talk about that race, because it's a beautiful story about how modern physics actually gets done, not by lone geniuses scribbling on blackboards, but by enormous international collaboration spending years underground, painstakingly reducing every source of error, all to measure one number. The basic idea behind measuring theta 13 was elegant, and it went back to nuclear reactors. Remember how Raines and Cowan first detected neutrinos using a reactor back in 1956? Well, half a century later, physicists returned to reactors for a completely different reason. Nuclear reactors produce enormous numbers of electron antineutrinos, just floods of them, pouring out from all those fission reactions happening inside the core. And if theta 13 was non-zero, then some of those electron antineutrinos should oscillate into other flavors over a specific distance. The trick was figuring out how far away to put your detector and how precisely you could measure the disappearance. Here's what makes this particular measurement so tricky. The oscillation driven by theta 13 happens over a relatively short distance for reactor neutrinos, roughly 1 to 2 kilometers from the reactor core, and the expected disappearance signal was small. Not the dramatic 1/3 deficit that Ray Davis saw with solar neutrinos. We're talking about maybe a few percent of the electron antineutrinos going missing. A few percent. That means your detector has to be incredibly well calibrated, and you need to account for every possible systematic error that could mimic or mask that tiny signal. The solution that several groups converged on was to use 2 detectors, a near detector close to the reactor and a far detector at the optimal oscillation distance. By comparing the neutrino flux at both locations, you could cancel out most of the uncertainties about exactly how many neutrinos the reactor was producing in the first place. You're not measuring an absolute number anymore. You're measuring a ratio, and ratios are much more forgiving of systematic errors. It's a clever trick, and it's one of those ideas that sounds obvious in hindsight, but required years of careful analysis to get right. 3 major experiments took up this challenge, and they were spread across the globe. There was Double Choose in France, near the Choose nuclear power plant in the Ardennes region. There was Reno, the reactor experiment for neutrino oscillation, in South Korea, near the Hanbit nuclear power plant. And then there was Daya Bay in southern China, near the Daya Bay nuclear power complex in Guangdong province, not far from Hong Kong. Now, of these 3, Daya Bay had some significant advantages. For one thing, the Daya Bay complex has 6 powerful reactor cores, which means an enormous antineutrino flux. More neutrinos means more data, faster. The experiment used 8 identical detectors arranged at different distances, 2 near detector halls close to the reactors and 1 far hall about 1.6 kilometers away, tucked under a mountain that provided shielding from cosmic rays. The mountain above gave them something like 860 meters of water equivalent overburden, which is a measure of how much rock is sitting above you, blocking the constant rain of muons from cosmic ray showers in the atmosphere. Those muons are a nuisance. They can produce signals in your detector that look like neutrino events if you're not careful. The detectors themselves were beautiful pieces of engineering. Each one was essentially a nested set of cylindrical vessels. At the center, you had a transparent acrylic vessel filled with 20 tons of liquid scintillator, a special organic liquid doped with gadolinium. Gadolinium is a rare earth element, and here's why it matters. When an electron antineutrino interacts with a proton in the scintillator through inverse beta decay, it produces a positron and a neutron. The positron immediately annihilates with an electron, producing a prompt flash of light. The neutron bounces around for a few microseconds and then gets captured by a gadolinium nucleus, which then releases a cascade of gamma rays. A second, delayed flash of light. So you're looking for a very specific signature. 2 flashes of light, separated by a characteristic time delay. That double pulse signature is your golden channel. It lets you pick out genuine neutrino events from the enormous background of other things happening in your detector. Surrounding the central scintillator vessel was another acrylic vessel filled with undoped liquid scintillator, which acted as a gamma catcher, capturing gamma rays that might escape the inner volume. Around that was a stainless steel vessel filled with mineral oil, and embedded in that outer vessel were photomultiplier tubes, those incredibly sensitive light detectors that can register a single photon. Each detector module had 192 of these photomultiplier tubes, all staring inward, waiting for those telltale flashes. And the whole assembly was immersed in a pool of ultra-pure water, instrumented with more photomultiplier tubes, serving as both a shield against external radiation and an active cosmic ray veto. If a muon came crashing through the water pool, the photomultiplier tubes would see the Cherenkov light it produced, and the data acquisition system would flag that time window and throw out any coincident signals in the inner detector. Layers upon layers of protection against false signals. It's the kind of meticulous, almost obsessive attention to systematic errors that defines modern particle physics. The DUNE collaboration involved something like 200 scientists from 6 countries, and they began taking data in late 2011. And they moved fast. By March of 2012, they had their answer. Theta 13 was not 0. It was small, yes, about 8.5 degrees, much smaller than the other 2 mixing angles, but it was definitively, unmistakably, non-zero. The statistical significance was beyond 5 sigma, which in particle physics is the gold standard for claiming a discovery. 5 sigma means there's less than a 1 in 3.5 million chance that the result is a statistical fluke. Reno in South Korea announced a consistent result just weeks later, and Double Choose, which had started with only a FAR detector initially, had already seen hints the previous year. But DUNE got there first with the most precise measurement, and it was a moment of genuine excitement in the physics community. Now, you might be thinking, okay, so they measured an angle. Why is that such a big deal? And here's where it gets really interesting. Remember, if theta 13 had been 0, then the CP violating phase in the PMNS matrix would have been physically meaningless. It would have dropped out of all the equations. There would have been no way for neutrino oscillations to behave differently for neutrinos versus antineutrinos. But theta 13 being non-zero, even though it's small, means that CP violation in the neutrino sector is possible. The door is open, and CP violation matters enormously because it might help explain one of the deepest mysteries in all of physics. Why does the universe contain matter at all? Here's the problem. In the Big Bang, energy should have produced equal amounts of matter and antimatter. And matter and antimatter annihilate each other on contact, converting back into pure energy. So, if everything were perfectly symmetric, all the matter and antimatter created in the Big Bang would have annihilated, leaving a universe filled with nothing but radiation. No atoms, no stars, no planets, no you and me. But obviously, that's not what happened. There's a tiny excess of matter over antimatter, roughly 1 part in a billion. And that leftover sliver is everything we see, every galaxy, every grain of sand. For this asymmetry to have arisen naturally, you need certain conditions laid out by the Russian physicist Andrei Sakharov in 1967. One of those conditions is CP violation. The laws of physics must treat matter and antimatter slightly differently. We know CP violation exists in the quark sector. It was discovered decades ago. But the amount of CP violation we've observed in quarks isn't nearly enough to explain the matter-antimatter asymmetry of the universe. Not even close. So physicists have been looking for other sources of CP violation, and the neutrino sector is one of the most promising places to find it. That's why Theta 1-3 being non-zero was such a big deal. It didn't prove that neutrino CP violation exists. It just proved that it could exist. Measuring whether it actually does exist requires a whole new generation of experiments, and that's exactly what's being built right now. But let's pause for a moment and appreciate something. By around 2012, the neutrino mixing picture was remarkably complete in its broad outlines. 3 flavors, 3 mass states, 3 mixing angles all measured, 2 mass square differences determined, and yet some truly fundamental questions remained unanswered. We knew the mass squared differences, meaning we knew the gaps between the squared masses of the 3 mass states, but we didn't know the actual masses themselves. We didn't know the absolute scale. Are neutrinos a fraction of an electron volt? A few hundredths? A few tenths? We knew they were tiny, far lighter than any other known massive particle, but pinning down the actual number has proven extraordinarily difficult. And there's another puzzle that sounds almost absurd when you first hear it. We don't even know the order. We know there are 3 mass states. Call them mass 1, mass 2, and mass 3. We know mass 2 is slightly heavier than mass 1 because of how solar neutrino oscillations work. But mass 3? We don't know if it's the heaviest of the 3 or the lightest. If mass 3 is the heaviest, that's called the normal ordering, or normal hierarchy, as physicists sometimes say. If mass 3 is actually the lightest, that's the inverted ordering. And this isn't just a bookkeeping question. The mass ordering affects how neutrinos interact with matter as they travel through the Earth. It affects the interpretation of CP violation measurements, and it has implications for cosmology, for neutrinoless double beta decay searches, for our understanding of the fundamental structure of particle physics. So how do you figure out the mass ordering? One approach is to study how neutrinos behave as they pass through matter, specifically through the Earth. When neutrinos travel through rock, they interact with the electrons in that rock via the weak force, and this interaction modifies the oscillation pattern in a way that depends on the mass ordering. It's called the MSW effect, after Mikhaev, Smirnov, and Wolfenstein, who worked it out in the 1980s, the same effect that turned out to be crucial for understanding solar neutrino oscillations. For long baseline experiments, where you shoot a neutrino beam hundreds of kilometers through the Earth's crust, the matter effect creates a subtle difference between normal and inverted ordering that, in principle, you can detect. And this is exactly what the next generation of experiments is designed to do. There are 2 enormous projects under construction right now that represent the cutting edge of neutrino physics. One is called DUNE, the Deep Underground Neutrino Experiment, based in the United States. The other is Super-Kamiokande in Japan, the successor to Super-Kamiokande. Both are staggeringly ambitious, and both aim to answer the questions that the previous generation of experiments left open. DUNE is particularly fascinating from an engineering perspective. The neutrino beam will be generated at Fermilab near Chicago, and it will travel 1,300 kilometers straight through the Earth. No tunnel, just rock, because neutrinos barely interact with anything, to a massive detector located nearly a mile underground at the Sanford Underground Research Facility in Lead, South Dakota. That's the same facility, by the way, in the old Homestake gold mine where Ray Davis ran his solar neutrino experiment decades ago. There's a lovely continuity to that. The mine that hosted the first deep underground neutrino experiment is now hosting one of the most advanced neutrino detectors ever conceived. The FAR detector at DUNE will consist of 4 modules, each containing 17,000 tons of liquid argon. Liquid argon is kept at minus 186 degrees Celsius, and when a neutrino interacts with an argon nucleus, it produces charged particles that ionize the argon atoms along their paths. An electric field applied across the detector volume drifts those ionization electrons sideways toward arrays of wire planes, where they're collected and read out. The result is essentially a 3-dimensional image of the neutrino interaction, a detailed photograph of the particle tracks, reconstructed from the pattern of arriving electrons. It's like a bubble chamber from the 1950s, but operating on a scale and with a precision that would have seemed like science fiction to the physicists of that era. The engineering challenges are immense. Keeping 70,000 tons of argon in liquid form requires enormous cryogenic systems. The purity of the argon has to be extraordinary. Contaminants at the level of parts per trillion can absorb the drifting electrons before they reach the wire planes. The detector modules are being assembled in vast underground caverns that had to be excavated from solid rock at the 4,850-foot level of the mine. And the whole thing has to run stably for decades, because accumulating enough neutrino interactions to make precision measurements of CP violation requires years and years of patient data taking. Super-Kamiokande, meanwhile, takes a different technological approach, but with equally breathtaking scale. It's a water Cherenkov detector, like its predecessor, but much, much bigger. A cylindrical tank 68 meters in diameter and 71 meters tall, holding 258,000 tons of ultra-pure water, instrumented with about 40,000 photomultiplier tubes. The sheer volume dwarfs Super-Kamiokande, and it will receive a neutrino beam from the J Park Accelerator Complex in Tokai, 295 kilometers away. The shorter baseline compared to DUNE means it's less sensitive to the matter effect, but it compensates with enormous statistics. More neutrino events, faster. Both experiments are expected to begin full operation in the mid to late 2020s, and the physics community is holding its breath. Because if CP violation in the neutrino sector is large enough, these experiments should be able to detect it. And if they do, it would be a clue, not a proof, but a genuine clue, toward understanding why the universe is made of matter rather than nothing. But neutrino mass itself remains a puzzle that goes deeper than just measuring a number. The thing that really keeps theorists up at night is not what the neutrino masses are, but why they're so absurdly small. Every other particle that has mass in the Standard Model gets that mass through its interaction with the Higgs field, and the mechanism works well. It explains the masses of quarks, charged leptons, the W and Z bosons. But if neutrinos got their mass the same way, you'd expect their masses to be roughly in the same ballpark as other leptons, or at least not wildly different. Instead, neutrino masses are at least 1,000,000 times smaller than the electron mass, and possibly much more. That enormous gap demands an explanation, And the leading candidate is something called the seesaw mechanism, which is one of the most elegant ideas in all of particle physics. The idea goes something like this. Imagine you have a seesaw on a playground. A real, physical seesaw, the kind with a plank balanced on a fulcrum. If one end is very, very heavy, the other end gets pushed way up high. The heavier one side is, the lighter the other side effectively becomes. That's the basic intuition. In the seesaw mechanism, you start by assuming that neutrinos actually do couple to the Higgs field in a perfectly normal way, just like every other fermion. That coupling would give them a mass, call it a Dirac mass, that's roughly comparable to other particles, maybe something in the range of the electron mass, or even heavier. Nothing weird so far. But then you introduce a second kind of mass, a very large one, associated with a new hypothetical particle, an extremely heavy right-handed neutrino that we've never observed directly. This particle would be so massive that it exists at energy scales far beyond anything our current accelerators can reach. We're talking about masses on the order of 10 to the 14 or 10 to the 15 giga-electron volts. That's approaching the grand unification scale, the energy where the fundamental forces of nature might merge into a single force. And here's where the seesaw comes in. When you write down the mathematics of how these two mass terms interact, the ordinary Dirac mass and the enormous Majorana mass of the heavy right-handed neutrino, you find that the resulting physical neutrino, the light one we actually detect, ends up with an effective mass that's roughly the square of the Dirac mass divided by that huge Majorana mass. So if the Dirac mass is something like 100 giga-electron volts, and the heavy Majorana mass is something like 10 to the 14 giga-electron volts, you get an effective mass of about 100 squared divided by 10 to the 14, which works out to about 10 to the negative 10 GeV, or roughly a tenth of an electron volt. And that's exactly the ballpark of neutrino masses that oscillation experiments suggest. The heavier you make the right-handed neutrino, the lighter the left-handed neutrino becomes. One end of the seesaw goes up, the other goes down. It's beautiful, really, and it's one of those ideas that feels almost too clean to be a coincidence. But, and this is important, the seesaw mechanism is a theoretical framework, not an established fact. We have no direct evidence for these heavy right-handed neutrinos. They're predicted by the math, and the math is compelling, but nobody has seen one. They'd be far too heavy to produce at the Large Hadron Collider or any accelerator we can currently imagine building. So how do you test an idea like that? Well, one way is indirect. The seesaw mechanism, in most of its forms, predicts that neutrinos are what physicists call Majorana particles. And that's a distinction worth spending a moment on because it touches on something genuinely strange about neutrinos, something that separates them from every other particle of matter we know. Every charged particle in the Standard Model, every electron, every quark, is a Dirac particle. That means the particle and its antiparticle are distinct. An electron and a positron are different things. They have opposite electric charge, so you can always tell them apart. But neutrinos have no electric charge. They have no color charge either, so there's no obvious quantum number that distinguishes a neutrino from an antineutrino, except, in the Standard Model as originally constructed, lepton number, which is a kind of bookkeeping label. Ettore Majorana, that brilliant and enigmatic Italian physicist who vanished so mysteriously in 1938, proposed back in 1937 that a neutral fermion could be its own antiparticle. A Majorana particle is identical to its antiparticle. If neutrinos are Majorana particles, then the distinction between neutrino and antineutrino is not fundamental. It's just a matter of the particle's handedness, its spin orientation relative to its motion. And that has a profound consequence. If neutrinos are Majorana particles, then a process called neutrinoless double beta decay should be possible. Let me unpack that. Normal double beta decay is a real, observed process. It happens in certain isotopes where a single beta decay is energetically forbidden, but two simultaneous beta decays are allowed. Two neutrons in the nucleus convert to two protons at the same time, emitting two electrons and two antineutrinos. It's rare, but it happens, and it's been measured. The half-lives are extraordinarily long, on the order of 10 to the 19 or 10 to the 21 years. But with enough material and enough patience, you can see it. Now, if neutrinos are Majorana particles, there's a variant of this process where the antineutrino emitted by one beta decay is absorbed as a neutrino by the other. The neutrino is its own antiparticle, so it can play both roles. The result is that two neutrons convert to two protons, two electrons come out, but no neutrinos at all, neutrinoless double beta decay. And the signature is clean. Instead of the two electrons sharing energy with two invisible neutrinos, they carry away all the energy themselves. You'd see a sharp peak at a specific energy in your detector, right at the Q value of the decay. Finding this peak would be monumental. It would prove that neutrinos are Majorana particles, confirm that lepton number is not a conserved quantity, and provide a direct measurement related to the absolute neutrino mass scale. Something oscillation experiments alone cannot do, since oscillations only tell you about mass differences. A whole generation of experiments has been searching for this signal, and so far, nobody has found it. But the searches are getting more and more sensitive. Experiments like Gerda and its successor Legend, using germanium-76 enriched detectors deep underground, and Camlanzen in Japan, using xenon-136 dissolved in liquid scintillator, and Cuore at Gran Sasso, using tellurium dioxide crystals cooled to just above absolute zero. All of these are pushing the limits. The current best limits on the half-life of neutrinoless double beta decay are above 10 to the 26 years. The next generation aims to reach 10 to the 28 years, which would probe the parameter space, where the inverted mass ordering predicts a signal. If the mass ordering is inverted, meaning the two heavier neutrinos are close together and the lighter one is well below, then the effective Majorana mass should be large enough that these experiments could see it. If they don't see it, that would be strong evidence for the normal ordering, and it would push the Majorana mass into a range that's much harder to probe. So you see how everything connects. The mass ordering, the CP phase, the absolute mass scale, the Majorana versus Dirac question. These aren't separate puzzles. They're all facets of the same underlying mystery. And the experimental program of the next decade or two is designed to attack all of them simultaneously, from different angles. There's another way to get at the absolute neutrino mass, and it's beautifully direct. You just measure it. You look at the beta decay of tritium, hydrogen-3, the heaviest isotope of hydrogen, and you very carefully measure the energy spectrum of the emitted electrons right near the endpoint, the maximum energy an electron can carry away. If the neutrino were massless, the spectrum would extend all the way to the endpoint and drop sharply to zero. But if the neutrino has mass, even a tiny mass, the spectrum gets distorted just below the endpoint. The electrons can't quite reach the maximum energy because some energy has to go into creating the neutrino's rest mass. The effect is incredibly subtle. you're looking for a tiny distortion in the last few electron volts of a spectrum that spans about 18,600 electron volts. It's like trying to detect a slight change in the shape of a coastline by standing on a mountain 100 miles away. The experiment designed to do this is called CATRIN, the Karlsruhe Tritium Neutrino Experiment, located in Karlsruhe, Germany. It's been running since 2019, and it uses an enormous spectrometer, a stainless steel vessel about 24 meters long and 10 meters in diameter, that was so large it had to be shipped by barge up the Rhine and then transported on a special road convoy through the German countryside. The spectrometer uses electric and magnetic fields to act as a very precise energy filter for the beta electrons. Only electrons with energy above a certain threshold make it through to the detector. By scanning that threshold across the endpoint region, CATRIN maps out the spectral shape with extraordinary precision. As of their latest results, CATRIN has set an upper limit on the neutrino mass of about 0.45 electron volts, which is already the most stringent direct measurement ever made. They're aiming to push that down to around 0.2 electron volts by the time the experiment finishes its full data-taking campaign. And there are proposals for next-generation experiments. Project 8, for instance, which would use a completely different technique, measuring the cyclotron radiation emitted by individual electrons spiraling in a magnetic field that could potentially push sensitivity down to the level needed to detect the minimum neutrino mass allowed by oscillation data, around 0.01 to 0.05 electron volts. Think about what that means for a second. We're talking about measuring a mass that's less than 1/10,000,000th of the electron mass. A mass so small that for decades, the smartest physicists in the world assumed it was exactly zero. And now we have machines precise enough to weigh it, or at least to close in on it from above, squeezing the allowed range tighter and tighter. There's something else worth mentioning here, something that connects neutrinos to the largest scales in the universe. Cosmology. The cosmic microwave background, that faint afterglow of the Big Bang, and the large-scale distribution of galaxies both carry imprints of neutrino mass. Because neutrinos were produced in enormous numbers in the early universe, and because they move very fast, they're hot, dark matter. They tend to smooth out the clustering of matter on small scales. The more massive they are, the more they smooth things out. By comparing precise measurements of the cosmic microwave background, particularly from the Planck satellite, with surveys of galaxy clustering, cosmologists can set upper limits on the sum of all three neutrino masses. The current cosmological bound is roughly 0.12 electron volts for the sum, though the exact number depends on which datasets you combine and what assumptions you make about the cosmological model. That's an astonishingly tight constraint, and it's already in tension with some interpretations. If the mass ordering is inverted, the minimum sum of masses would be around 0.1 electron volts, which is right at the edge of what cosmology allows. So cosmology might end up telling us the mass ordering before the particle physics experiments do. Or the two approaches might converge at the same time, cross-checking each other. And this brings us to something that I find quietly thrilling about where neutrino physics stands right now. For most of its history, neutrino physics was a field of patience and frustration, decades between prediction and detection, decades of the solar neutrino problem with no resolution, painstaking experiments in mines and tunnels, waiting years for a handful of events. But right now, in this decade, we're entering a period where multiple major questions might actually get answered. DUNE and Super-Kamiokande will probe CP violation and the mass ordering. CATRIN and its successors will close in on the absolute mass. Neutrinoless double beta decay experiments will test whether neutrinos are Majorana particles. Cosmological surveys will provide independent mass constraints, and there are even more exotic possibilities on the table. the question of whether there are additional neutrino flavors beyond the three we know about, so-called sterile neutrinos, which would not interact via any of the known forces except gravity. Hints of sterile neutrinos have appeared and disappeared in various experiments over the years, most notably in anomalies at the LSND experiment at Los Alamos in the 1990s and the Mini-Bueni experiment at Fermilab, which saw excesses of events that didn't quite fit the three-flavor picture. But other experiments have contradicted those hints, and the situation remains unresolved and honestly a little messy. The micro-DUNE experiment, using liquid argon technology that's essentially a prototype for DUNE, has been scrutinizing the Mini-Bueni anomaly, and so far hasn't confirmed it in the way you'd expect if sterile neutrinos were the explanation. So maybe it's something else, some poorly understood background, some subtle detector effect, or maybe it's genuinely new physics that we just don't understand yet. And that uncertainty, that openness, is part of what makes neutrinos so captivating. They've surprised us at every turn. Every time physicists thought they had neutrinos figured out, massless, simple, just a bookkeeping particle to balance the energy budget, neutrinos turned out to be stranger and more interesting than anyone expected. They oscillate. They have mass. They might be their own antiparticles. They might hold the key to why matter exists. And there's one more thing about neutrinos that we haven't really talked about yet, something that connects them not to particle accelerators or underground detectors, but to the most violent events in the universe, supernovae, the explosive deaths of massive stars. And this is one of the most astonishing things about neutrinos, something that sounds almost impossible when you first hear it, so let's take our time with it. When a massive star, say 8 or more times the mass of our sun, reaches the end of its life, it has spent millions of years fusing lighter elements into heavier ones. Hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage burns faster than the last. Hydrogen fusion lasts millions of years. Silicon fusion, the very last stage, lasts about a single day. And at the end of that day, the core of the star is made of iron, and iron is a dead end. You can't extract energy by fusing iron. The nuclear furnace that has held the star up against its own gravity for its entire life simply stops. And what happens next takes about 1 second. 1 second. The iron core, roughly the size of Earth but containing more mass than the sun, collapses. It falls inward at roughly a quarter of the speed of light. The density shoots up until protons and electrons are squeezed together to form neutrons and neutrinos. Enormous numbers of neutrinos. The collapsing core reaches nuclear density, roughly 200 trillion times the density of water, and then it suddenly stiffens, like a ball of rubber being compressed until it can't compress any further. The infalling material bounces off this newly rigid core, sending a shock wave outward. And you might think that shock wave is what blows the star apart. But here's the thing. The shock wave stalls. It runs into the still infalling outer layers of the core and loses energy. It gets stuck, maybe 100 or 200 kilometers out from the center. If nothing else happened, the star would just quietly collapse into a black hole. No explosion. No supernova. So what revives the shock wave? What actually blows the star apart and scatters all those heavy elements? The carbon in your body, the oxygen you breathe, the iron in your blood. Out into space? Neutrinos. The collapsing core produces such an absurd quantity of neutrinos that even though each individual neutrino barely interacts with matter, the sheer number of them, combined with the extraordinary density of the material just behind the stalled shock wave, means that a small fraction of those neutrinos, maybe 5%, maybe less, deposit their energy into that region, and that energy is enough. It re-energizes the shockwave, pushes it outward, and the star explodes. The entire visible explosion of a supernova, all that light, all that kinetic energy of the expanding debris, represents only about 1% of the total energy released. The other 99% is carried away by neutrinos. Think about that. When you see a supernova in a telescope, that spectacular galaxy-outshining flash of light is a rounding error compared to the neutrino burst. The real event is invisible to your eyes. It's a neutrino event, and we've actually detected this. On February 23, 1987, a star exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years away. It was called Supernova 1987A, and it was the closest observed supernova since Kepler's supernova in 1604. But before the light reached us, actually a few hours before the optical brightening was noticed by astronomers, neutrino detectors on Earth picked up a tiny handful of neutrinos from the explosion. Kamiokande 2 in Japan, the same detector that had been watching solar neutrinos, detected 11 neutrino events in a burst lasting about 13 seconds. The IMB detector, the Irvine, Michigan Brookhaven experiment in a salt mine in Ohio, detected 8, and the Baksan detector in Russia detected 5. That's it. 24 neutrinos total, out of the roughly 10 to the 58th power. That's a 1 followed by 58 zeros. Neutrinos that the supernova emitted. The rest passed through Earth as if it weren't there. They passed through every planet, every star, every galaxy in their path without noticing. But those 24 were enough. Those 24 neutrinos confirmed, in a single 13-second burst, the basic theoretical picture of core collapse supernovae that physicists had been developing for decades. The total energy carried by the neutrinos, extrapolated from those 24 detections, matched the predictions beautifully, roughly 3 times 10 to the 46 joules, which is about 10% of the rest mass energy of the Sun, released in neutrinos in a matter of seconds. The timing was right. The energies of the individual neutrinos were right, peaking around 10 to 15 million electron volts. It was a stunning confirmation of our understanding of how massive stars die, and it opened up the field of neutrino astronomy, the idea that you could learn about astrophysical events not from their light, but from their neutrinos. Masatoshi Koshiba, who led the Kamiokande experiment, shared the 2002 Nobel Prize in Physics partly for this detection. And it's worth noting how personal this was for him. Koshiba had spent years building and improving Kamiokande, originally designed to look for proton decay, then repurposed for solar neutrinos. When SN 1987A went off, his detector was ready. If the supernova had happened a few years earlier, before the upgrades that made Kamiokande sensitive enough, those 11 neutrinos would have gone unrecorded. Timing matters in science, and sometimes you get lucky. Now, SN 1987A happened in a nearby dwarf galaxy. If a supernova were to go off in our own Milky Way, and one is statistically overdue, the last one visible to the naked eye was in 1604, modern detectors would see not 24 neutrinos, but tens of thousands. Super-Kamiokande alone might detect 8 to 10,000 neutrinos from a supernova at the center of our galaxy, about 26,000 light-years away. IceCube, the enormous neutrino detector at the South Pole, a cubic kilometer of Antarctic ice instrumented with over 5,000 light sensors, would see a massive collective signal. And there's actually a global network called SNOOS, the Supernova Early Warning System, that links neutrino detectors around the world so that if multiple detectors see a burst simultaneously, an automated alert goes out to astronomers worldwide, telling them to point their telescopes in the right direction. The neutrinos arrive hours before the light does, because they escape from the core immediately, while the shock wave takes hours to reach the star's surface and produce the optical brightening. So neutrinos give us advance notice. They're cosmic messengers that arrive before the main show. And this connects to something even more profound about the role neutrinos play in the universe. We talked earlier about how neutrinos might explain the matter-antimatter asymmetry through leptogenesis, the idea that heavy Majorana neutrinos in the early universe decayed asymmetrically, and that asymmetry was converted into the excess of matter over antimatter that we see today. But neutrinos also shaped the universe in another way. In the first few minutes after the Big Bang, during Big Bang, nucleosynthesis, when protons and neutrons were combining to form the lightest elements, hydrogen, helium, a little lithium, neutrinos played a critical role in determining the ratio of neutrons to protons. That ratio, which was about 1 neutron for every 7 protons by the time nucleosynthesis got going, was set by weak interactions involving neutrinos. And that ratio determined how much helium the universe produced, about 25% by mass, which is exactly what we observe. If neutrinos behaved differently, if there were more or fewer neutrino flavors, or if their interactions were slightly stronger or weaker, that helium fraction would change, and the universe would look fundamentally different. In fact, Big Bang nucleosynthesis provided one of the earliest constraints on the number of neutrino flavors. By the late 1970s and early 1980s, cosmologists realized that adding extra light neutrino species would increase the expansion rate of the early universe, which would freeze out the neutron-to-proton ratio at a higher value, which would produce more helium. The observed helium abundance was consistent with 3 neutrino flavors, maybe 4 at a stretch, but not 5 or 6. This was a cosmological argument made before the particle physics confirmation. Then in 1989, experiments at the LEP collider at CERN measured the width of the Z boson and determined that it decays into exactly 3 types of light neutrinos. 3, not 2, not 4. The cosmological prediction and the particle physics measurement agreed beautifully. That's the kind of cross-check that gives you confidence the whole framework is solid. So neutrinos are woven into the fabric of the universe at every scale. They helped determine the chemical composition of the cosmos in its first minutes. They power the explosions that forge heavy elements and scatter them into space. They might explain why matter exists at all, and they're streaming through you right now. About 100 billion of them pass through every square centimeter of your body every second, mostly from the sun, and you never feel a thing. There's also a background of neutrinos left over from the Big Bang itself, the cosmic neutrino background, analogous to the cosmic microwave background radiation, but even older, dating from about 1 second after the Big Bang, when neutrinos decoupled from the rest of matter. Those relic neutrinos have cooled to a temperature of about 1.95 Kelvin, colder than the microwave background, and they fill all of space. We haven't detected them directly yet. Their energies are so fantastically low, about a 10,000th of an electron volt, that no current detector can see them. But there's an experiment called Ptolemy at Princeton that's trying to develop the technology to do it, using tritium capture. If they succeed, it would be like listening to the very first whisper of the universe, a signal from a time before atoms existed, before light could travel freely, from the first second of cosmic history. And maybe that's a nice place to let all of this settle. We've come a long way together, haven't we? From Wolfgang Pauli's desperate, almost apologetic letter in 1930, proposing a particle he thought might never be detected, to Rayna's and Cowan's patient work at a nuclear reactor in the 1950s, finally catching those ghostly interactions. From Ray Davis sitting in a gold mine in South Dakota, counting a handful of argon atoms and trusting his results even when the theorists said he must be wrong, to the massive water detectors in Japan and Canada that finally proved neutrinos change flavor on their journey from the sun. From Pontecorvo's lonely theoretical insight about oscillations, decades ahead of its time, to the beautiful mathematical framework of the PMNS matrix that describes exactly how the three flavors mix and transform. From the puzzle of why neutrinos have mass at all, something the Standard Model never predicted, to the seesaw mechanism and the tantalizing possibility that neutrinos are Majorana particles, identical to their own antiparticles, a property that no other known fermion possesses. Every step of this story has been a surprise. Every time physicists thought they understood neutrinos, the neutrinos had something new to say. They were supposed to be massless. They're not. They were supposed to travel in fixed flavors. They don't. They were supposed to be a minor bookkeeping particle. They might explain the existence of all the matter in the universe. And there are still surprises waiting. The mass ordering, the CP violating phase, whether they're Majorana or Dirac, whether sterile neutrinos exist, whether the anomalies that don't quite fit are pointing us towards something genuinely new. DUNE will start taking data in the coming years, sending neutrinos from Fermilab through 1,300 kilometers of rock to South Dakota. Super-Kamiokande is filling with water in Japan. Juno is being assembled in China. Legend and Camlanzen and next-generation double beta decay experiments are pushing toward the sensitivities they need. Katrin is refining its mass measurement, and Project 8 is developing entirely new techniques. Cosmological surveys are mapping the universe with enough precision to weigh neutrinos from the sky. It's a remarkable time. The tools are finally catching up to the questions. But even if you drift off right now and forget every detail, every name, every date, and that's perfectly fine. That's what this is for. Maybe just hold on to this one feeling, that the universe is stranger and more subtle than it looks, that the most elusive, most ghostly, most nearly nothing particle we know of turns out to be deeply important, that sometimes the quietest voice in the room is the one worth listening to the most carefully. Trillions of neutrinos are passing through you right now, right this very moment, as you lie here. They've traveled from the heart of the sun, or from a reactor on the other side of the world, or from a supernova that exploded before our solar system even formed. They carry information about the deepest processes in nature, and they ask nothing of you. They just pass through, gently, silently, on their way to somewhere else. And there's something oddly comforting about that. This constant, invisible river of particles flowing through everything, connecting the sun to the earth, the stars to the void, the first second of the universe to this quiet moment right now. You don't have to think about it anymore. Just let it be there, in the background, like the neutrinos themselves, and rest